Hi, in this video, we'll be covering concepts of 2D projectile motion. We'll be covering like the time of flight, maximum height achieved, and range. And all of these we'll be understanding with the help of a simulation like this. So let's get started. So what happens when a projectile is launched? It has two components of velocity. The first component of velocity is the horizontal component, and the second component is the vertical component. So let us say this is the projectile, and it's launched at an angle of theta with an initial velocity of u. So its initial horizontal velocity would be u cosine theta, and the initial vertical velocity would be u sine theta. As this projectile goes up, it reaches the highest point. At the highest point, it has to turn back and start falling down. So the vertical velocity actually goes to zero at this point. The only force that's acting on the projectile throughout the motion is the gravity, mg. So hence we can assume that the only acceleration will be downwards. This means that the horizontal velocity u cosine theta is constant throughout the flight. So let's apply the kinematic motion equation to the vertical velocity component. And let's say it takes a time t to reach the highest point. So we can say that zero, which is the velocity, vertical velocity at the highest point, equals u sine theta minus gt, because the acceleration is acting downwards opposite to the direction of the velocity, vertical velocity. So this will give us t equals u sine theta upon g. So this is half the time of the flight, the time to reach the highest point. The total time of the flight is time it takes from the beginning to the end to when it falls down on the ground. So that would be equal to 2t or 2u sine theta upon g. So this is the total time of flight. And this is exactly what we saw. 2u sine theta upon g. And this came out to 2.89 seconds as we launched the projectile with an angle theta equals 45 degrees and u equals 20 meters per second. And you can calculate this and confirm it with the solution provided here. Now, the second concept here is the range that the projectile covers. So let's see how to get that. Since the horizontal velocity is constant throughout the flight, I can say that ux times the total time of flight gives me the range. And hence, u cosine theta times 2u sine theta upon g. And using the trigonometric identity that 2 sine theta cosine theta equals sine 2 theta, I can get u square sine 2 theta upon g as the range of this projectile. Now we need to find out the maximum height. So how do we do that? The maximum height is the height that it takes to fall from the highest point to the lowest point. At the highest point, the vertical velocity is zero. And it takes a time equal to u sine theta upon g to get there. So I can say that the maximum height achieved is u sine theta times t minus half g times t square. And remember the t here I'm using is half the time of flight, the time taken to reach the highest point. And this would be equal to u square sine square theta upon 2g. So these are the three formulas that we derive for projectile motion. Now let's have a look at simulating these things. We come to the simulation here, and I'll be sharing this in the description of the video. You can play and get an intuitive feeling for how projectile motion works. Let me try and change the initial velocity. Let's try and make it about 40 meters a second. And let me try and change the angle of projection to 30 degrees maybe. Right. And I'm trying to make it 30 degrees here. All right. So if I launch it here, oops. Yeah. So let's see the three parameters that we derive here. Range, 141.39 meters. Height, u square sine square theta upon 2g equals 20.41 meters. Time of flight, 2u sine theta upon j equals 4.08 seconds. I encourage you to calculate these with the values given. So the values given here are u equals 40 meters a second and sine theta, or rather theta equals 30 degrees. So we can plug these into the values. With this, we'll get the time of flight as 2 times 40 times sine theta upon g, and the range as u square sine 2 theta, which will become 60 degrees upon g, and the height would be u square sine square 30 upon 2g. And we can calculate these and see if they match the values given in the simulation. And I'd encourage you to play the simulation for various values, try and derive these formulas and confirm that when we plug in the values, we indeed get the same values that the simulation provides. All right, so that was 2D projectile motion in a jiffy. And I hope the simulation helps you understand this intuitively. And you can post your doubts on my video, and I'm sure to answer them. Thank you very much.